Today we will talk about rate detection algorithms on C and C++ native language. We are trying to figure out which related works have been done before us, and yeah, we are trying to choose some distinguishable samples among many of them. First of all, we have looked race that Google's product. It's in a way so complicated implementation, and we are trying to have non-instrumented overhead with some hardware support. They call it PMU, Performance Monitoring Unit, and they are simply extra registers trying to handle operating system signals between kernel and user side. I will just simply show you. Yeah. They are trying to not to have some overheads because of instrumentation of runtime cores. They are trying to handle this with hardware support, as I said, PMU. And their motivation is when they have two threads and they are trying to synchronize these two threads execution with PMU signals, but the complication of the implementation comes from two sides. One is which signal will be dispatched to which instruction. As you see, two signals are gathered from thread 1 and dispatched to instruction write 2, but they have to be sure about that. This is one complication, and I think the other one is I have forgotten.
I have a simple question.
Yeah.
We are using PIN for instrumenting the C program,
Mm-hmm.
and they have the PMU for instrumenting their C program, right? So they are using
they are not using PIN.
Using PMU for gathering these events.
Using PMU for they don't have instrumentation.
Okay.
We don't have any instrumentation here. We just have inserting signals from inserting signals from application side to the kernel side. When you want to have a write operation, you just throw signals. An operating system signal handler dispatches to the CPU and gathers the signals back from CPU and dispatches to the application side. I mean, application side, but as you said, which thread, which instruction will be dispatched from the signal is really complicated to handle. Yeah, we don't have any instrumentation.
What are those signals? Are they interrupts?
Yeah, interrupts.
Okay.
Mm-hmm. Can you scroll up? I want to see if you go on. this one. This is what they have implemented instead of having pin tool. This is hardware, it's kind of hardware extension, and they're trying to synchronize these instructions, applications, user level instructions with this hardware extension. It is somehow really so complicated.
So PMU is something like a buffer of communication medium? What is it exactly?
Yeah, it has buffers, hardware buffers, and they are trying to collect signals from application side. And when the buffer is filled, then they dispatch to the CPU.
Okay, so
But the problem is that you have to be sure that this signal will not be dispatched to this instruction before this unlock operation is done. You see, if you do this, then you are not sure that this Y2 is is raised because I mean we are trying to be sure about that. I mean we are not sure that this lock and unlock is really what we thought in other implementations like POSIX stretch and stuff. We have hardware support, and this hardware support can override all user level POSIX stretch and some other stuff. So PMU signals should ensure that this dispatching signal will be executed after this unlock operation. This should be. But what they provide us is that. So yeah, I have one more. I mean, yeah. The important thing is that you can have this. You can ensure the applications happens before, in a way, happens before relation with these signals by putting here a stall NOP operations and wait to. I mean, you are trying to be satisfied that this has enough kind of NOP operations, which shows us like barriers at the end of the write operations, and we are after that. Okay, this is released, and we can dispatch this signal. But NOP operations are not the safest way to handle this stuff, this signal dispatching. So they are really, they have really complicated register sets to handle all of this stuff. But they say that they are really simple hardware extensions. But they are really genius guys because they are Google guys. So, and then there are some important trade-offs about race Z. Just show. I want to show you. As you see, this is our traditional method. Changing. Maybe you could zoom. Yeah. Oh, is it fine? Yeah. Yeah. this is traditional way of instrumenting synchronization stuff with dynamic instrumentation tools. And we have log synchronization and synchronization primitive. So we call binary instrumenter, modified binary instrumenter called for log, and this is the conventional way. But what PMU has is that where we have again synchronization primitives, and we are handling these synchronization primitives by instrumenting them in a conventional way, just as pin or some other stuff. But we are handling write and read operations by these hardware extensions. We are dispatching operating system signals and getting them back. And because synchronization calls are not so frequently. I mean, reading and writing operations are so frequently, and having instrumentation calls for all read and write returns as a big overhead. So they thought that we can handle it with hardware. But as you see, well, there's a big trade-off. As we all know, we cannot run this kind of race detection tools while running time of program. I mean, the whole running time of program. So we have to run this race set in some time intervals, time slices. So how this? Yeah.
Why can't we run hardware always? So what's the cost?
What is cost? They don't. I mean, operating system handling and dispatching. Can you just think that you are coming from kernel side to the user level side, and big context switching, switching register, all that stuff again, and yeah, this is really a big overhead. I mean, you should have, hardware support is in a way improvement, but it again has great overhead. If you do that so frequently, I mean, during the whole runtime of program. I mean, yeah, you in a way mentioned the trade-off.
Şurada beyaz bir yere gidelim.
What we want to have is catching races. This is this is whose runtime?
Oh. Huh? Oh, that was right.
And this is number of races code. So this is our quality parameter. Uh, of course, when you think performance, uh, this whole runtime is execution time of this PMU, right? Ratio. This execution time of ratio, if it increases, then we have our overhead of handling operating system signal handler overhead increases. And this means that our quality parameter decreases. And yeah, but if we run it, you know what, more, then we have the chance of catching more races. Yeah, you got the trade-off, right? Okay. Okay. This is the, yeah, this is probability analysis. The overall impression of race that is.
You can say races.
Races.
Yeah.
Mm.
Very lucky. Anyway.
Then I wonder whether I
So,
some
you are trading off precision and race detection actually by turning off hardware, right?
Right.
Okay. So,
And you said in the beginning that they don't have the instrumenting overhead, or they don't think about the instrumenting overhead.
so
They don't have instrumentation call and return. I mean,
for
kind of
variables.
pin tools, dynamic calling function for instrumentation.
So how does it?
Yeah, we have to see the result.
How does the tool know when to open runtime state?
This is probably.
So it just
This is what I have written here.
it just opens in a time and
Yes.
then
Yes.
press it.
It says that even a fixed template to
Yeah.
fix something in a just
Implementation is really so complicated, but the report is so simple.
yeah,
Close and open. But I think they can be trunk while
the trick is I think the hardware expansion of using
yeah.
hardware.
What is that signal speed problem? There's a signal speed problem. What is that?
Sample skip problem. Signal, not signal. Sample skip.
Okay.
I think
You are considering for the signal speed anyway.
Yeah.
Simple.
Can you zoom
Instruction
controllers?
and instruction n+1 signal receive.
This is okay. Where? This is our user code application level. Okay. This is our middleware, yes. And we will have kernel side, right? Yeah. When instruction M is being executed, the instruction counter always increases, and during this side, as you said, when, during these intervals where PMU is being executed, it is just collecting samples by recording, right? And when the read or write operation is being handled, then interrupt is delivered. So, and when the interrupt is being converted to the user side, then signal handle will handle it. I have some results.
PMU gets its input when sampling is open, and when sampling is closed, PMU sends signal.
Yeah, right. Yeah. Sampling is just can be handled while PMU is running. When it's closed, you cannot.
PMU doesn't send any signal, but it's really nothing to
PMU. Yeah, it is implementation detail, but PMU sends signals. PMU takes signals from CPU to dispatch to the user level. I'm just thinking as operating system signal handling. Yeah. Yeah, this is running longer. We have so many samples, so we are on the side of having more precise rate detector, but this means that we are also having overhead of signal handling. I want to show you they have so many optimizations like operating system sampling, offline. Offline. There should be. It should be somewhere.
Maybe offline zoom out.
Yeah, offline. They are using hardware registers of Intel and AMD, and they are having assembly instrumentation tool MAO for analyzing these special registers.
Okay.